Hello students, welcome to a new lecture. So in the last lecture we had started the topic of torsion and we had arrived at this expression. So here psi is the warping function. So we said that warping function has to satisfy this equation. So this is an equation that consists of two derivatives with respect to x and with respect to y, because warping function we assume that it is a function of x and y, and it is a meaningful assumption. So it is not possible to solve this equation on its own because there are two variables involved. So let us bring in some more condition, or at least one more conditions pertaining to warping function. So for that I will use this famous equation which I taught you in the third lecture of probably this course, which is Cauchy's formula. So just to give you a mental recap, I have downloaded a figure from internet. So you remember this? So if you know the stresses on three orthogonal planes, then you can determine the stresses on any plane which is oriented at any arbitrary orientations, provided you know the direction cosines of the outward drawn normal on the plane. So that Cauchy's equation, which is valid for all bodies in equilibrium, we'll use it. So this is the equation. So this equation I have written currently in the notation I have explained in class. So that was based on Srinath book. Uh, so when we apply to this problem, uh, maybe we will slightly change the symbols and things like that, but that will come to that. So we'll try to use Cauchy's equation to get one more condition, so that together with this equation we can solve for the warping function. So again consider a surface on the on the outer surface of the section. So remember, this is the problem that we are trying to solve. Again, it is a general shape, not necessarily a circular shape. So you consider any a surface along the height, along the z direction. So its plan will be an area, right? So that is what I have drawn here. So this is that general section, and remember it is subjected to only a twisting load at the end. So when you are talking about a general cross section at any height, it is free of load. Okay, so you consider the surface generated by a point moving from this point to here. So this is initial point, this is final point. So as a result of that, it traverses a x distance of minus dx, and because along x coordinate it is reducing the coordinate, and along y it is dy. So this is the surface for which we are trying to apply the Cauchy's formula. So remember, again I will show you. See, in this case also, this is the three-dimensional surface for which we had applied or derived the formula of Cauchy's. So you can also refresh the derivation, things like that, using your notebook. So remember, it is free of load. So Tx and Ty and Tzn are nothing but the forces along the three coordinate axes. Now in this case it is a free surface, there are no forces. So Tx and Ty and Tzn, they are zero, there are no normal stresses, there are no force, external force actually along the boundary. So one more thing we can say is, see, this is the surface, right? So on this surface, the outward drawn normal is like this. So your z-axis is perpendicular to the plane of paper, which means angle made by z-axis and the outward drawn normal from the surface is 90 degree. So nz, which is nothing but the direction cosines to x direction along x-axis, it is 0 because it is cos 90, it is 0. So nz is 0, these external stresses are 0, which means in this Cauchy's equation this is 0, this part entirely becomes 0, so only this part is remaining, out of which in the last lecture we had already seen that sigma x, sigma y and sigma z are 0. So this is 0 and this is 0, and in addition tau xy is also 0. So tau xy is also 0. So only non-zero equation is the third one. So you will have only two terms. So that is what I have written here. Following the notation of Timoshenko, we will write nx equal to L, ny equal to m, and nz equal to n. I think I have used it before also. So what happens is the Cauchy's equation, first two equations are identically satisfied. The third equation simplifies to tau xn, tau xz L plus tau yz m. Okay. Now what are L and m that we will try to arrive at? So remember, L and m are the direction cosines of outward drawn normal. Now if it is the direction cosines of this surface itself, we can easily find out, because it's the component along x is dx by ds, minus dx by ds, and component along y is dy by ds. But we want the this Cauchy's formula, it is the direction cosines of the outward drawn normal. So it will be reverse. So along x direction it will be dy by ds, where ds is this length, and along y direction it is minus dx by ds. So use these expressions, substitute into this equation. This is the equation. Now tau xz and tau yz, you already know what they are. We had arrived at it in the previous lecture. So this expression you can substitute it for tau yz and tau zx, and that's what I have done here. So if I use this and substitute in this equation simplifies to this. Okay. So again, this is one more equation in which the variable is warping function. So this equation combined with our first expression, which is this. These are the two expressions using which you will solve for the warping function. So two equation, variable is one only, but since it is a function of two coordinates, you need two equations. So using these two equations, you can solve for warping function. Now second equation is also like a boundary condition. That's why I written a BC here, because you see the expression ds. Because what's happening is we had written the Cauchy's equation for the element which is on the outer surface, right? So the second expression is like a boundary condition, but in any case these are the two expressions using which you will solve for the warping function. Now when you determine warping function, you can go back to the expressions. So this is how we started, right? So you will have u, v, you will have w. So you can solve for u, v, w, using which you can find out strain and stresses. Okay, so this is the solution for a general torsion problem for a cross section which is non-circular. Because for if it is circular, it will be a subset of this, a simplified version of this, where warping function won't be there. So this is the solution. Now let us try an alternate procedure. So there is also an alternate procedure using the classical approach of using stress function. Okay, remember we had dealt with stress function earlier. So let us try to solve or arrive at these equations in terms of stress function. Okay, so that's what we'll do. So for that, let us take this expression, which I think we had obtained it in the last lecture. So remember, in the last lecture we were trying to solve this differential equation of equilibrium, and these two were identically satisfying, and only this equation was non-zero, and we got that this plus this equal to 0. So I'll start with that expression. Now so keep in mind, what all we try to do with a stress function. So always with a stress function, what we said is stress function is a function denoted by any symbol. We denoted it so far with phi, using which we can represent the different stresses of the problem, and which also satisfies the conditions of solution. Okay, so we need to get a stress function phi, using which we can represent tau xz and tau yz. So remember, all other stresses are 0. Out of the 6 stress components, these are 0, this is 0, only tau yz and tau zx is not 0. So following the concept of stress function, tau xz and tau yz, we should be able to represent it by this stress function phi, and the stress function also should satisfy all the conditions associated with the problem. So this is one condition, right? So this condition can be satisfied if you take stress function of the following form. So if you take tau xz as d phi by dy and tau yz as d phi by dx, then we can see that easily when you substitute these two expressions in this equation, it will be satisfied. Okay, so phi phi is that stress function. So if phi is a valid stress function, then tau xz is this and tau yz is this. Okay, now let us substitute it into the originally expression. So remember, this is the expression for tau yz and tau zx. We had arrived in the previous class. So you substitute the expressions of this into that equation. So this is what we'll get. So these are the expressions. So you will get expression in terms of phi, in terms of stress function. Now in this equation there is warping function. So the solution using warping function we already arrived at here. Okay, now we are trying to arrive at a solution which does not involve warping function. So what we have to do is, let us try to eliminate warping function. So what we will do is, here there is del phi by del x, this is del phi by del y, again not phi, actually it is psi or chi, whatever, but just don't follow my pronunciation, just follow this symbol. Okay, so here there is a derivative with respect to x, and here there is a derivative with respect to y. So to cancel out a warping function from the expression, what we'll do is we'll take the derivative of this expression with respect to y. So that here there is del square by del x del y, and second expression we will take derivative with respect to x. So there will be del square by del x del y again, and then we will subtract both. So in doing so, we can eliminate the warping function. So that is what I done here. Take the derivative both and subtract them. So when you subtract, this minus and the subtraction minus will cancel, and this is the expression that you get. So it means del square phi by del x square plus del square phi by del y square equal to minus 2g theta. So 2g theta, you can write it in terms of another variable f. So this is the expression. So this is the first expression that we are looking for. So this expression is a replacement of this expression. So this expression is in terms of warping function, but what we arrived at now is a expression in terms of stress function. Okay, now similarly we have to arrive at the equivalent expression for second expression in terms of stress function. So let us do that. So what we'll do is we'll start from this equation. So this equation, remember, we had arrived it based on Cauchy's equilibrium equation. So this expression, right? So in this expression, let us try to substitute. Let us try to write it in terms of stress function. So uh, tau xz and tau yz, we had already written it in the following form, right? So when you substitute that in this expression, it will simplify to this. Okay, so this is nothing but the expanded form of d phi by ds. So this is the chain rule of this derivative, right? Because phi with respect to y into dy by ds plus phi with respect to x into dx by ds, right? So this is the second expression we were looking for. Again, since it is derived from this, which is the boundary condition, remember we stated that this is the boundary condition, right? So this is the, this expression also you can say it is like the boundary condition. So these two expressions that we just derived forms the solution of torsion problem in terms of stress function. Okay, so once again I'll say this two expressions is the solution of torsion problem in terms of warping function, and same expressions in terms of the classical approach of using stress function. These are the two equations. So any solution of stress function which satisfies these equations form the solution. So as you can see, the boundary condition using stress function is much more simpler than that of warping function. Okay, and there is also a physical meaning for this second expression. It means that the stress function phi along the boundary is constant, because when you are getting the derivative of stress function with respect to boundary, remember s is the boundary, right? I'll go to that. This is ds, so s is the boundary. So derivative of stress function with respect to s is 0 means stress function is constant along the boundary. So this is the equations using which you can solve for stress function, which will be using which you will get the final solution for the torsion problem. Now the nature of stress function, if you recollect what all we did so far in Cartesian coordinate system and polar coordinate system, different types of problem, there will be different types of stress function, right? So just like that, here what happens is, depending upon the type of cross section, whether it is rectangular, triangular, elliptical and all, the phi, nature of phi will vary, but ultimately the phi, whatever it is, whichever cross section it is, it should satisfy these equations which form the solution. Because once you determine phi, you can determine tau xz and tau yz, which forms the complete solution that we discussed. Okay, so that is about it. Now a small part is remaining, I will complete that also. Now up till this point we have written everything in terms of the torsional rotation. Remember, we are trying to solve this problem, right? Now this rotation or torque will happen only when there is a moment or a torsion or a twist at the ends, right? So let us try to write the formulations of the problem in terms of the external twist. So that is what I have tried to do here. So for that, let us consider a section at the ends, either at the bottom end or top end. Okay, so the intermediate locations are free of forces, but at the bottom and top you will have external moment, right? This is the external torsional moment. There will be a reaction here. Now if you take any point on the surface, either on the bottom surface or top surface, we can again apply the Cauchy's equation. So for that, what we will do is, see, remember this is the Cauchy's equation. So what happens is, since we are taking a point or an area on the outer and upper and top and bottom surface, outward drawn normal is parallel to z-axis. Okay, so as a result of it, what happens is n, or the direction cosines of outward drawn normal with respect to z-axis, it will be 1. It will be plus 1 or minus 1 depending upon which section you are taking, because remember it is the outward drawn normal. So if you are taking the section in the bottom, outward drawn normal, it is along positive z-axis, so it is 1. Along this side it is along the negative z direction, it is minus 1. L and M are 0. Okay, because the outward drawn normal, remember it is perpendicular to the plane of this paper, right? So it is perpendicular to x and y axis, so they are 0. So substituting these into Cauchy's equation and also using these values of stresses, what you get is, you will get two equations. One is x bar, or the force along x direction, and force along or stress along y direction. So that will be plus or minus tau xz, and y is plus or minus tau yz. Okay, you can just substitute it here. So this is the equation you have to substitute. Okay, now plus or minus I have written because, as I told you, n can be plus or minus depending upon which surface you are taking. Okay, so this is x and y. Now we have to arrive at an expression of this, arrive at an expression in terms of external moment. Okay, so what is that moment? So remember, this is just one element. Okay, so you have to do integration of that element. So for that also, the moment caused is stress or force into lever arm. Okay, so about this axis it is y bar into x, and about this axis it is x bar into y, and both are along opposite directions, right? So the net moment mt, you can write it as y bar into x minus x bar into y dx dy, which is the area of the element. You double integrate it. Now y bar and x bar, what you do is, it is in terms of tau xz and tau yz, which we already know in terms of the stress function. Okay, so you substitute that into the expression, then use the integration by parts, and when you are doing one other variable you fix, make it as constant. So using this rule and using the condition that phi is 0 along the boundary. Remember, phi we said, since d phi by ds is 0, it is constant, right? So using that condition, what we get is, we will get that mt, which is the axial moment or axial torsional moment, equal to 2 times double integration phi into dx dy. Okay, so this is the complete solution. Okay, complete solution actually is this one only. This is the two equation you can, using which you can find the solution. But this part is all about writing the axial moment or axial torsional moment in terms of stress function. Okay, so I hope you have understood the lecture. If you have any doubts, please let me know. So as I told you many times during the classes, advanced solid mechanics is such a subject that you have to take it easy. Okay, it is interesting if you have the aptitude, but anyway, so what I first suggest is, you read what is given in Timoshenko book, because here it will be like the summary. Okay, so first try to go through what is in the Timoshenko textbook, and then when you have doubts, only you come back to the handwritten notes. Okay, if you have any doubts, please let me know. Thank you.